Selcuk Uluagac, professor in the Department of Electrical and Computer Engineering at Florida International University. He'll be presenting Detecting Counterfeit Smart Grid Devices. Welcome, Selcuk, please.
Yeah. Thank you, Zachary. So, hello, everybody. My name is Selcuk Uluagac. I'm a member of the faculty at Florida International University. It's actually a university in Miami. And I'm also the director of Cyber Physical Systems Security Lab. And this is a joint work with my postdoc, Dr. Aksu, and then my PhD student, Leonardo. The title is System-Level Approach to Detecting Counterfeit Smart Grid Devices. So I also need to acknowledge the fact that this is a US Department of Energy supported project. So we have many projects under this consortium with so many other collaborating universities. So this is one of the projects under that, under that side. So, so let me briefly give you, information about, first of all, who I am and what we are doing in this lab, and brief overview of our activities. So basically, in this lab, I founded this lab 2 years ago when I moved from Georgia Tech about 2.5 years ago, and so we have about 10 students in the lab, and we're working in the problems basically related to the security and networking of IoT systems, CPS systems, and and we have so many other different projects. So this is just one of them. And today's talk, I have 3 parts. First, I know you are all maybe familiar with the background information for the smart grid, but I'll be giving you okay, I need to learn how to use this. I'll be giving you a little bit of background information, and then we're going to be looking at the technical approach for this work, and then finally I'm going to be sharing the results with you. So this is the smart grid domain, and in this infrastructure, it's a complicated infrastructure with heterogeneous, interconnected, so many different networking equipment and applications. So we have from basically 3 components, from generation, transmission to distribution. We have different power resources. We have transmission substations and microgrids, etc. And we have distribution network, and then we have the customer premises. We can also, from the networking perspective, we can also classify this infrastructure based on neighborhood area networks, wide area networks, and home area networks. So when we look at this infrastructure, what we see here is that there are a lot of devices and there are a lot of applications running. So for the purposes of this work, we are classifying the devices into 2 categories. One is resource-limited devices, and the other is resource-rich devices. Resource-limited devices are devices with simple hardware and software architecture on them. And examples of these, for example, with lowest performance CPUs and very limited memory resources, like PLCs, RTUs, etc. And resource-rich devices, these are close to maybe full-scale computing systems. They have faster and even multi-core processors with significant cache and RAM resources. So why are we interested in this problem? So currently, counterfeiting is basically a big problem. It amounts for at least 7.5 billion in lost revenue for US semiconductor companies. So we are looking at this problem in the smart grid domain, and this has not been extensively studied, and also our approach is really different from the others. So just a quick summary of our contributions, basically, of this work. We provide a system-level approach, system-level look at the counterfeiting problem. We are not solving the problem at the hardware. We are looking at the OS level, and I'm going to be explaining and talking to you about the adversary model and then the details of the framework, and I'm going to be also sharing the performance overhead. So let's talk about the details of the approach. So we mostly, since I'm coming from the academia, but I was also briefly in the industry, we like, first, we like first talking about what we are dealing with, what problems. So here we are addressing when we have a counterfeit device. We have an adversary model where we have a counterfeit device can leak the information to another device or outsider parties, or the counterfeit device can poison the measurements, like for example the status of the network or the load and demand information, or a counterfeit device can store the information and send it to another third party later. So these are the different threats that we are considering in our framework. So, as I told you before, we have two different devices, like resource-limited devices and resource-rich devices. So, considering these two device types and considering these three different adversaries, we have 6 different counterfeit devices in our model to deal with. So each of these counterfeit devices, basically in our framework, they are messing up with either the memory or the open extra communication channels, or they poison the measurements, etc. So I have to also let you know that we didn't have an actual counterfeit device. So since we didn't have an actual counterfeit device, the best approach that we could do was to model the behavior of an attacker. So for this, we came up with a stochastic process, and we modeled the adversary's behavior with Poisson distribution. So basically, the attacks happened according to the Poisson distribution. Well, in reality, they might be behaving more deterministically, or they might be behaving with another distribution. They may be, but on average, Poisson allows us as a good stochastic approach. So we built a small test bed. In fact, it's very tiny, and at FIU, we have a very big smart grid testbed. It's like maybe the size of this room, with different generators from generation to transmission and distribution, where we can have different configurations. But this one, particularly for this study, we wanted to focus on the device, so we had a small, very tiny testbed. So what we did, we used the open source version of the IIC 61850. It's and then we utilized the publisher-subscriber two-way communication model of the GOOS messages. So basically, here we had a Raspberry Pi for a resource-limited device, and we had a laptop here for the more powerful resource device. So they communicated between each other, GOOS publisher and GOOS subscriber model. Okay, so in our framework, we have 3 steps. First step is the data collection step. The second step is the data processing, and the third step is the decision, whether the device is a counterfeit device or a genuine device. In the data collection step, we trace and capture all the system calls associated with the applications that are running on the device. Then, in the data processing step, we have 3 simple detection approaches. Basically, we are utilizing correlation mechanisms, like statistical correlation as our feature, as our main detection mechanism. It's simple. You will be surprised, even if it's so simple. Like, you could add maybe other, in the future we are actually, thinking of other detection mechanisms as well. But even with this simple, we were able to, catch a lot of counterfeit devices. In the detection module, as I said, we are basically deciding whether the device is genuine or a real device. So, in this first, we compare the system calls made from the counterfeit device to the ground truth device, and based on the type of frequency of the system calls, we collect that information. And then we have for resource-rich devices, we have we are applying a statistical correlation in a simple way, and then we apply the same technique with a slight difference from the simple one, and on the resource-limited devices. So basically, at this step, we look at the order of the system calls that are triggered by the system. So, just as a reference, this is the autocorrelation function and definition, and this is for the correlation for the counterfeit device detection that we use. So here we have the genuine device and we have the unknown device. So for our framework, we collect the data, the system calls, function calls, etc., all these calls, and then that information is passed to the data processing step, system call list comparison, and then we do the simple and advanced. So we don't do all these detection mechanisms all at once. So we do it step by step. So that also allows us to save energy, and then finally we decide whether the device is counterfeit or genuine. Here is the method that we utilize for to extract information for the genuine device. So let me discuss the results, how this simple technique is really useful. And we ran our model for 30 times for all these different counterfeit devices and in different settings. And the result that I'm going to be sharing is basically the average of these 30 different runs of the experiments. So let's look at the here results. So these are the average amount of system calls per type normalized against the system call lists of the ground truth device. So value over 1 indicates the presence of counterfeit device, basically. Here we have the p-trace, below here we are the library interposition. So these are system call techniques to capture the system calls that you can use. And as you see here, these values for the second counterfeit device and the third counterfeit device for the resource-limited case, our simple method, the first method, is not really successful. So I'm going to show you how the correlation mechanism then comes into place and then actually makes it better. I'm going to show you. Here, we apply it on the resource-rich devices. Again, we have this, this problematic region, and for both p-trace and library interposition. As I was telling you, this is really at the system level, not at the hardware level. Our assumption is basically for doing that, whatever the hardware, if it's a fake components, it's going to either communicate or do something malicious that would be observable at the system level. That's our assumption. So yeah, let's continue. And when we apply the simple correlation techniques, you see that we are able to improve the results here that we haven't. So here we have the on the resource-rich devices, and here again there is some problematic region. So the way that we do is that we have a threshold value. These are all configurable values, by the way. 0.6. Any value above 0.6, basically blue bar, refers to its ground truth device, and these are basically the ones that are picked up by our system as the counterfeit devices. Here, for the resource-limited device, for the interpositioning case, our simple correlation, the first of the correlation, doesn't identify the counterfeit devices. However, when we applied our advanced statistical correlation technique on that, on this one, we see that our system is able to identify these devices again. So as I said, we apply these in a cascading fashion, not on only all of them at once, and to be able to utilize the resources efficiently. So finally, okay, I'm good on time. Perfect. Finally, so we looked at the overhead on the system resources on our using our framework. Here on the left, you see the costs associated, real-time, system time, user time, memory, CPU, when there is no framework for the resource-rich devices and resource-limited devices. On the right, you see with the framework, using the techniques on the resource-rich, resource-limited devices. As you see, these are the percent increases, and we really do not have a lot of impact on the resources. This is simple. So just to summarize, with these simple techniques, with the correlation, statistical techniques, we are able to really pick up and identify the counterfeit devices in our with respect to our adversary model. The overhead is not that high, and we have really a comprehensive adversary model with different threats, and in fact, our model, this framework, could be applied to other settings as well, not only here for the smart grid devices. I think we could also improve our work by incorporating other detection mechanisms, which at the moment we are actually working on. This is actually an ongoing work. So we could test it with more devices, and I know it's hard to find a real counterfeit device. I know it's hard to find a fake iPhone or fake other phones, or even you can find fake routers or routers that are leaking information to some other entities that are not supposed to be doing it but doing it. But for smart grid domain, I think this is a kind of a unexplored yet not explored problem. And another thing is that I think that I already mentioned to you is that the adversary may be behaving not according to the Poisson model. Poisson is a good stochastic model. On average, it's good to utilize it in to look at the general and generic behavior, capture the generic behavior. But in realistic cases, the adversary might be more deterministic, or even maybe using a different distribution too. So let me conclude. Counterfeit devices constitute a serious threat to healthy and secure distribution of data in the smart grid. And we designed and implemented a system-level framework. It's a system-level framework capable of monitoring and detecting counterfeit smart grid device behavior. We have a realistic adversary model that would be able to capture different threats, and we have really good results, and it doesn't propose a significant overhead. In the future, we will incorporate, as I said, machine learning algorithms as a detection mechanism, and other detection approaches like CPU and memory utilization. We will be also incorporating that into our results. Some references to in this one in work that I noted, and so I want to thank you very much, Zachary and all. If you have any questions, this is my end slide, and I'll be happy to answer.
Questions? So I have one in the back. Hello, is the mic on yet? I can't tell. Hello,
Did
microphone.
I black it? Did I black it? Did you black it? Yeah. Can we show this last slide? Yeah.
Hello, Parnia Najafi from FireEye.
I'm sorry, I can't hear.
Microphone.
can we put up the last slide? Yeah, thanks.
Is that what?
Yeah, yeah.
So, Pioneer Najafi from FireEye.
Hello, are we checking the mic yet? Got a mic?
Okay, perfect.
All
yeah.
right, good.
Okay, so what was your success rate? You said that you had very good detection, but what was the rate of that?
Success rate?
Yeah.
Okay, so yeah, that's a good question. Like, I have the results for the accuracy. We have about like 98% accuracy, but I didn't include into the slides. It's right now being published. It's under review. So, but we have really good results. The approach is really simple, like using some statistical techniques from signal theory, DSP, and yeah.
Sir, question?
Yeah.
Thanks. Yeah, really great work. But
Thanks.
in your test bed, I would say that you have an idealized example of the level of instrumentation that's available in a practical system deployment. And system call level data is very, very rare to be seen as an interface provided by vendors in deployed industrial control systems. So
Exactly, yeah.
what is do you have a message maybe for vendors of encouragement for providing this level of instrumentation and forensic data, both at maybe process call level, process execution level, and system call level?
Yeah, it's a great question. Yeah, our difficulty really was being able to, have access to the real smart grid devices, and they are also, it's really closed source and closed, everything closed in this realm. And but the methods are, as computer scientists or computer engineers, we know how to deal with the problem. And gladly, we were able to find open source version of the substation protocols that are used by these devices, the IAC 61850. Lib, it's called, if you Google it, you'll be able to find it. So it was really straightforward to install and, in a tiny device and have our own, simple, tiny, test bed. Like we do in other projects in the rest of the other, when we deal with the real world threats, if we have the open source, we deal with the threats better because the code is, watched and everybody's watching the code. And so I think the message is that if we have more open source products, then we would be able to, academicians, students, any enthusiast, anybody would be able to come and check it for you and then let you know, and then we would be able to have the same mechanisms that we have for the, the internet. So that's my message, actually. So, yeah.
Question?
Because we know how to deal with the problem. Yeah.
Waiting from ProtectWise. I have two questions, actually, fundamentally. So you used 6 counterfeit devices. Where did you get that devices? And how do you know that the counterfeit devices use different system calls compared to the genuine devices? Because you assumed, implied that part first.
Yeah, that's a great question. But as I explained in my slides, we assumed that, so at the end of the day, a counterfeit device is going to do something. Okay? It's going to either store the information or it's going to steal the information, which you can Google, and even you can come up, some real examples. Like there were some labs that they discarded their routers because that were manufactured by a specific, specific vendor. So they were leaking information. So at the end of the day, a company, a device, a vendor, basically, is going to be doing, when it has a corrupt, hardware components, at the end of the day, it's going to do one of those 3 things: steal, or leak, poison. And in order to do these things, you have to mess with the memory. You have to, open ports, and you have to communicate. You have to do some secret things. So we incorporated all those things in our model, and we are able to catch them at the system level. So that way, in realistic cases, we would be able to catch all these attacks. I don't know if this, but you're right, and I also told you, we don't have an example of a counterfeit device. We only are, that's one of the problems. We only know how it would behave, basically.
So are we talking about hardwares, right? We are talking about hardwares.
Yeah.
So like, for example, you are leaking some message, okay?
Yeah.
So the genuine device talk to the right IP address, but the counterfeit device is talking to another IP address. But for the system call part, maybe they are exactly the same.
I'm sorry, I didn't get it. I'm sorry.
I mean, if you are considering like some counterfeit devices is leaking the information,
Yeah.
right? So maybe the true devices are talking to set of the true IPs, and the counterfeit device is talking to another IP. Maybe it's a IP set by hacker. But for the system call part, okay, they should be the same. Just the IP address network, like your HTTP or DNS part may be different, but system calls may be same.
Yeah, I understand what you're asking, but I didn't go into the details. This is really high level of what we are doing, but we are incorporating all those, things in the framework. Like, we are looking at where this guy is communicating to, where is this, what is this guy doing, etc. But if you are as close, as possible to the hardware, okay, to catch the behavior, you're at a really, more advantageous, place. And at hardware, it's really hard to catch stuff at the hardware level because there are so many things happening. I mean, we have another project that we look at that. That's, in a separate project, but it's really not that easy at the hardware abstraction, and also for efficiency purposes as well. Yeah. Any other question?
I have a quick question or,
Yes.
or suggestion. So you're assuming in here also malicious counterfeits. Now, some counterfeits are just economic. They want to be able to sell you a device at full cost, but provide something that's much cheaper. And potentially just a performance metric in there may also be able to identify other types of counterfeits that are not maliciously storing or leaking data, but are just made with inferior components and not responding to the appropriate area. And I think a lot of our asset owners would be just as concerned about those types of components as they are about malicious counterfeits.
Yeah. Yeah. Yeah.
Any other questions? One back here.
Good. A lot of questions. Thank you.
I guess as well, if an attacker has gone to the trouble of counterfeiting a device and he's changing its behavior, like he's got some motivation, and it's just one extra step for him to feed back false data so that from the point of view of your algorithms, it looks like a legitimate device, but...
Yeah, it's a very good point. Actually, one of the next steps that we are going to be incorporating. We're going to be also incorporating this in a distributed fashion, like where we have more information. Also, look at this overall system view. Yeah.
So you get extra communication on the network or something like this, or?
I'm sorry, I didn't get. Okay.
So you'll pick up if there's extra data moving around the network and take that as an indicator of a change in behavior or something.
Yeah,
like
yeah,
this?
yeah, yep.